Okay, so now the next qualitative properties that we are going to look at is boiling point elevation. So when you said boiling point elevation, it means an increase in boiling points. So generally, in the case of boiling points, remember from my previous video that you will see how increase in the number of solid particles or increase in the number or increase in concentration of solid particles lead to decrease in the vapor quality. But in this case, as you add the number of solid particles into a solvent, it increases the boiling point of the solvent. Like for example, now we know that the boiling point of water is 100 degrees centigrade. But in a situation where you now add salt, if you now have your water, you have the pure water, and you add salt. So this addition of salt into the solvent leads to increase in boiling points. So it means that as you add the number of solids into the solvent, the boiling points increase. So that is why it's called boiling point elevation. So an increase in boiling points leads to, an increase in the number of solid particles into a solvent leads to increase in boiling points. So that is the meaning of boiling point elevation. So as you increase the number of solid particles, or as you increase the concentration of the solid particles, there will be an increase in the boiling point, and that is why it's called boiling point elevation. That is why it's called boiling point elevation. So now we have a formula, or let me just give an example. We have what we call molarity or molarity. And we have boiling points. We have molarity here and we have boiling points. So if you added 1 molar sodium fluoride, remember that the boiling point of water is 100 degrees centigrade. So now if you apply 1 molar sodium chloride, the boiling point will now be 101 degrees centigrade. It means that the boiling point is increased by 1. So as you increase the concentration of the solids, there will be an increase in boiling points. And another thing is like if we have 1 molar concentration of sodium fluoride, so the boiling point of water will be increased to 105 degrees centigrade. And so also at the same time, as we increase the molarity, the boiling point will be increased. So it means that the more you increase the concentration of the solid particles, the more the boiling point will be increased. And we have a formula for calculating boiling point elevation. And the formula for calculating boiling point elevation is delta T. Delta T is equal to Kp times molarity times I. And what is this I? The I here stands for Van Hoff constant, Van Hoff factor, Van Hoff factor. So we have Kb, which is a gyroscopic constant, and we have molarity, and we have what we call Van Hoff constant. Like for example, the Van Hoff constant of water molecule, of sodium chloride is 2, because when sodium chloride dissolves in a solvent, it will produce sodium ion plus chloride ion. So it means that we have 2 molecules of ions. So that is why Van Hoff constant in this equation will be 1. Van Hoff constant in this equation will be 1. So what is the formula for calculating molality? So the formula for calculating molality, how do you calculate molality? Molality. So we have formula for calculating molality, and the formula is moles of solutes divided by kilogram of solvent. Kilograms of solvent. So it means that in the case of molality, you can have a formula for calculating molality is equal to number of moles of solutes divided by the kilogram of solvent, and this is the formula for calculating molality. So in the case of boiling point elevation, as I said, boiling point elevation is a situation where when you are adding a solid particles, the boiling point of the solution will be increasing. So that is why it's called boiling point elevation. So like for example here in this case you have a fuel solvent and you now add to a solvent. So you now add to a solid. So as a result of that, the boiling point will be increased. And that is why here we show an example here where we have molality. When you have 1 molar sodium chloride, you add it into a pure water, then the boiling point will be increased by 1 degree centigrade. And if you have 5 molar sodium chloride and you add it into the water, then you now increase it to 105 degrees centigrade. So this is just a typical examples of how the boiling point elevation increases with an increase in the number of solute particles. So the next thing that you are going to look at is freezing point diffraction. So in the case of freezing point diffraction, from the word diffraction means lower, so lowering. So in the case of freezing point diffraction, it's a situation when you are adding your solid particles, the freezing point will decrease. Like for example, now we have also a formula here for calculating freezing point diffraction. The formula is delta T is equal to minus KF times molality times I. So the formula is delta T is equal to minus KF times molality times I. The KF, why KF is negative here, it's just to give an indication that the freezing point is decreasing. That is the essence of having minus KF. So minus KF is just indicating that the freezing point is decreasing. And the M here is molality, which is the number of moles of solute divided by the number of solvent. And the I here means Van Hoff's factor, which is dependent on the number of particles after dissociation. So now, for example, we have the KF of water, the KF of water is equal to minus 1.86. But remember, in normal sense, the freezing point of water is 0 degrees centigrade. So the freezing point of water is 0 degrees centigrade, and the KF of water, which is Kirchhoff constant, KF means Kirchhoff constant. So it's minus 1.86. It's minus 1.86 degree centigrade for water. And that is the Kirchhoff constant of water. But if there is a zero solute, the freezing point of water is 0 degrees centigrade. It's 0. So now, but what if you now add 1 molar sodium chloride? So if you add 1 molar sodium chloride, it means that your freezing point will be decreased by a factor. And how is it going to increase? I think you can just easily calculate. Since you know that the KF of water is 1.86 degrees centigrade per molar, so now I'm going to say minus 1.86 from the formula, and of course the molality is 1, then times I. What is our I? Our I, when this is sodium chloride, it will now break down to produce two ions, which is sodium chloride, sodium ion and chloride ion. So here we have two. So in 1 molar sodium chloride, when you add 1 molar sodium chloride, then the freezing point will be decreased by minus 3.72 degrees centigrade. So this is the freezing point differential. So as we add the number of solid particles, the freezing point will be decreasing. And let's say now, let's say we add 5 molar sodium chloride. So what will be the decrease in the decrease in the freezing point? So it's simple. We can just come here that we know that the microscopic constant of water is minus 1.86, then times what is the concentration? So the concentration is 5, and then we now have Van Hoff constant since the sodium chloride is 2. So at this point, the freezing point of water will be decreased by minus 18 points. It will be decreased by minus 18.6 degrees centigrade. So that is the freezing point differential. So this is how it is. So as you increase the number of solid particles, the freezing point will be decreased. And this is the formula for calculating decrease in freezing points. That is, the freezing point differential is minus KL ML. Okay? So the next colligative properties that we are going to look at is osmotic pressure. So under osmotic pressure is also another type of colligative properties that whenever you increase the concentration of the solid particles, the osmotic pressure increases. So it means that there's a direct relationship between osmotic pressure and the number of solid particles. So in this case, also, as you increase the number of solid particles in a solvent, the osmotic pressure also increases. And there is a formula for that, and this is just two. So osmotic pressure is represented with I, which is equal to M R. And the M here stands for molarity. So this one, in this case, we have molarity. Then we have R. The R here is universal gas constant. So the R stands for universal gas constant, which has a value of 0.08206 ATM liter per mole per Kelvin. So it's a constant which is something as 0.08206 ATM liter per mole per Kelvin. This T stands for temperature, and we have I here. So the I here stands for Van Hoff factor. So this is for osmotic pressure. So ladies and gentlemen, we are just going to look at some examples and exercises, and then you try them. I will solve like 2, and then you try and solve the others. Thank you. So we have one question here. That 1.65 gram of sodium chloride is added to 220 ml of water at 300 at 34 degrees centigrade. How will this affect the freezing point of water? Assume the sodium chloride completely dissociates in water, given that the density of water at 35 degrees centigrade is equal to 0.994 gram per mole. And our KF value is equal to 1.86 degrees centigrade kilogram per mole. So I think this one is simple. So to calculate the increasing point differentiation or the change in freezing point, you can now see change in freezing point for the freezing point differentiation is equal to KF molality than of function. So, but we already have KF, but molarity is missing, and one half constant is also not known. So how are we going to get this? So the first thing that we are going to do is to calculate molarity. Molar, so this is, and of course, if you remember molarity is equal to mole of the solutes divided by the kilogram of water. Because our solvent here is water. So divided by the kilogram of water. So already the number or the mass of the solute is given with the sodium chloride. So now the mass of sodium chloride is 31.65 gram. And of course, we are to calculate the molar mass of sodium chloride. And remember, the mass of sodium is 23, the molar mass of sodium is 23, and the molar mass of chlorine is 35.5. We have 35.5. So now we are going to add this, and we are going to add 23 plus 35.5. So we now have 58.5. So we have 58.5. So therefore, we are now going to say mole of sodium, mole of sodium chloride is now equals to 31.65 divided by 58.5 divided by 58.5. Okay? You now get the number of moles of sodium chloride, which is 0.54 mole. But now the next thing is to get the kilogram of water. Is to get the kilogram of water, that is the mass of water. But if you can see from the questions clearly, there is no mass of water. Rather, the volume of water is given and the density of water is also given. So you are going to use a formula for density is equal to mass all over molar mass. Sorry, the density is equal to mass all over volume. So we are going to use that and calculate the mass in kilogram. Okay? So from here we can see clearly the density of water is 0.99 kilogram per mole and the volume of water is 220 mil. So we are now going to calculate the mass, and remember the formula says density is equal to mass all over volume. So therefore now mass is equal to density times volume. So the density is 0.994 times the volume 220 mil. So therefore, we are now going to calculate and get our answer. So if you now press our calculator this time, we are now going to get 218.68. Now the density is in gram, and of course, so it means that here is in gram. So you have to convert it to kilogram because our formula, our amount of movement should be in kilogram. So we are now going to say divided by 1000. So if you now say divided by 1000, we are now going to have 0.219. Yeah, we can approximate 219 kilograms. So now we have our number of moles of sodium chloride and we have our mass of water in kilograms. So now 190 is now equals to 0.54 divided by this 0.219. And remember from our formula, it's from this formula, mole of solutes is already obtained, or we already got it as 0.54, and then the kilogram of water is 0.219. So we now divide this by this. So after we do that, we are now going to have 2 points. We are now going to have 2.47. So we have 2.47 mole per kilogram. So this is our molarity. So now we get molarity, and we already have KF here, but we don't know our Van Hoff constant. So remember, it's sodium chloride. So since the sodium fluoride will completely break down to produce sodium iron plus fluoride ion. So there Van Hoff constant here we have 1 and 1. So 1 plus 1 we have 2. So our Van Hoff constant is 2. Our Van Hoff constant is 2. So therefore we have now T delta F is equal to our KL is 1.86 times our M is 2.47, then times our I is 2. So after we now press this calculator, our calculator 1.86 times 2.47 times 2, we are going to get our final answer. So ladies and gentlemen, you can try this given that the KF of water is 1.86 Kelvin kilogram per mole. What is the freezing point of water if 14.9 grams of potassium chloride was dissolved in 125 grams of water? So try this. This is assignment. Let's try this. For this, another question. The solution is made by dissolving 13.0 grams of sucrose in 117 grams of water, producing a solution with a volume of 125 ml at 20 degrees centigrade. What is the expected osmotic ratio at 20 degrees centigrade? So I think it's simple. The analogy is I is equal to M R T I. So we are now talking about osmotic ratio. So of course we have to see the molarity and the R is constant. So molarity is mole of solids divided by the volume of divided by the volume of the solids. Divided by the volume of the solution. So this is the questions that we are now going to solve. So I think to calculate, so we are now going to say mole of solids. Our solid is sucrose and the mass of sucrose is 13 grams. So the mass of sucrose is 13.0 grams and the molar, so we have to calculate the molar mass. So the molar mass of sucrose is the molar mass of sucrose is now going to be 342 grams per mole. So now we are going to calculate the mass one. We are going to calculate the mass. We are now going to say what sucrose is equal to 13 divided by 342. 13 divided by 340. So after we now have number of moles of sucrose, we have that divided by 343. So we now have 0.0380 mole for the number of moles of sucrose. And then you already have the volume of the solution. So the volume of the solution is 124 ml. But we need the volume. The volume should be in liters. So the volume should be in liters. So how are we going to calculate the volume in liters? So we are now going to convert this one to liter. So we have 125 divided by 1000, which is now going to be 0.125 liters. So we now change it to liter. So from here we can just say so now we now have our volume in liter and we have our mole. So what we are going to do now, we are now going to say molarity. Molarity is equal to 0.380 divided by 0.125. So we are now going to take this and we divide it by 0.125. So we are now going to have 0.0415 liter. So we have this as our molarity, and then the next thing is our R value. So our R is constant, which is our R is equal to 0.0806 Kelvin. Okay, yeah, I think, yeah. So we now have this R is constant 0.0820 liter ATM per mole per Kelvin. And from the questions, of course, we have a temperature of 20 degrees. So 20 degrees, we convert it to Kelvin by adding 273. So we have 293 Kelvin. And of course, our solid here is sucrose. So sucrose is non-volatile. So our Van Hoff constant is 1. Our Van Hoff constant is 1. So now we apply the formula by calculate by using the formula which says osmotic radio is equal to molality times R times T times R. So our M is 0.304 times R, and our R value is 0.080206 times our T. Our T is 293 Kelvin. So once you press your calculator, the answer you obtain here is your osmotic pressure. So ladies and gentlemen, thank you for listening. If you did not watch my video, please go and watch it. Thank you. And we are going to continue as we are going to solve so many other examples. Thank you.